Welcome to this presentation with the title Econometrics for Data Scientists. What is econometrics all about? Econometrics is about learning from data. The goal is usually to make better decisions or to improve the design of institutions and policies. And obviously econometrics is also used in business, and there it's about in the end of the day, serving customers well, improving profitability, and so on. What is very important and is often stressed in econometrics is that there's a distinction between predictions and causal effects. And we're going to see later what exactly that means, but I want to say this already here. Econometrics is part of economics, and economics sees itself as a stringent social science in the sense that math is used to communicate ideas, so math is used to make things very explicit. What are the key principles in economics? What is certainly very important is that there's a separation between preferences and constraints, so what people want and what people can achieve. What is also very important is maximizing behavior, so individuals and firms try to do as well as possible given the constraints and given their preferences or objectives. And when individuals or firms interact, then this ultimately leads to allocations, and what one imagines to happen is that there's some sort of equilibrium that is stable over time. Now, what is econometrics, technically speaking? So one can think of it as the unification of economics and statistics. And I'm saying here unification because what is not meant, at least from the perspective of economists, is that we simply apply statistics to economics. So it's more than that. It's going beyond what is the standard set of topics in statistics in order to address very important questions. And this again often goes back to the distinction between prediction and causal effects or causality. And again, we're going to see later more formally what that distinction actually is. What I'm doing here in these slides is two things. First, I'm going to recap some basic concepts from statistics that are used over and over again in econometrics. And I'm going to talk about the most important tools in the econometrics toolkit. I'm going to do this, on a very superficial, in a very superficial way, but I think it's nevertheless useful to go through this once more in order to get the big picture of things and to be reminded of some of the things one has probably seen before. What are the main topics? More specifically, first of all, random variables, so some properties of random variables, and also what we can say about how they relate to one another when we have multiple ones, regression analysis, and instrumental variables estimation. So, random variables. Let's, for the moment, denote them by uppercase letters. So, for instance, X, Y, and Z. And each of them can take on values with associated probabilities. These probabilities are expressed in terms of something that's called a probability density function, or PDF. And I'm going to denote here the PDF of the random variable associated with the random variable x by f sub x, for y f sub y, and for z f sub z. Then there's also something that's called a cumulative distribution function, or CDF, and that would be the probability that a random variable is equal or smaller than a particular value. So these are going to be denoted by uppercase f sub x, y, and z, respectively. And random variables can either be continuous or discrete, or in fact, it can also be that they're a mixture of these two. Now let's look first at an example of a discrete random variable, say x. Let's say x takes on three values. It can be x equal to 0 with probability 0.2, x equal to 1 with probability 0.5, and x equal to 5 with probability 0.3. Note, first of all, that the probabilities sum to 1 when we add them up. Over all values this random variable x can take on. So we're going to have for 0, 0.2, for 1, 0.5, and for 5, 0.3. So we're going to have 0.2 plus 0.5 plus 0.3, and that gives 1. The density is f, little f sub x, evaluated at 0, so it's going to be 0.2. Evaluated at 1, it's going to be 0.5, and evaluated at 5, it's going to be 0.3, and this is just notation. And actually, I'm being slightly sloppy here, as in fact, the probability density function is called probability mass function for discrete random variables. So I have not been 100% precise, but the notation is perfectly fine with the little f. Now the cumulative distribution function is a step function, and that step function is going to have a jump at 0, where it jumps from 0 to 0.2. And at 1, it's going to jump to 0.7. What is 0.7? Well, 0.7 is 0.2 plus 0.5. It's going to give these 0.7. And at 5, I'm going to have 1. And that is not surprising, because 5 is the highest value x can take on. So what that means is, the likelihood that x is less than or equal than 5 is going to be 1, of course. And CDFs always have the property that they're weakly increasing. That means that the function is never going to go down when I move along the horizontal axis when I plot that CDF. Now next, what is a continuous random variable? So a continuous random variable can take on infinitely many values. For instance, all real numbers, or all real numbers in an interval. So for instance, all real numbers between 0 and 1, including 0 and 1. Now, when I say all real numbers in an interval, they're actually infinitely many. Because they're infinitely many, and intuitively the probabilities have to sum to 1, each individual level is obtained with probability 0. At the same time, there's going to be a positive probability that the values are in an interval of a length that is not 0. There's quite some math going on in the background, but in a nutshell, the density is related to the probability that the random variable is in an interval that is infinitesimally small. So that's all a little bit hard to imagine, what's much easier, in fact, is to think of the distribution in terms of the CDF. And then when one has that CDF, one actually gets the density function as the derivative of the CDF. And that again is related to something you might have heard before, namely that one can write down the CDF as an integral over values, and that will involve the PDF, and of course we know that the derivative of an integral is going to give us again the PDF in the end of the day. Next, let's talk about expectations and averages. So first of all, let's think about data. Okay, so we have data on one outcome, and these data are independent draws from the same distribution. So sometimes this is referred to as identical and independent, identically and independently distributed, or IID draws. And let's denote these draws by little x's. Okay, so we have the random variable capital X, and then I get many draws from that random variable capital X. So I'm going to denote them by little x1, little x2, little x3, up to little xn. So I'm going to have n draws in total. I can now take these n draws and calculate an average. So an average is calculated by summing up the values and dividing by the number of observations. So that's this formula here. And now it's important to simply realize or recap that this average actually estimates the expected value of x. And that expected value of x is denoted by E of x. Okay, so what that means in terms of terminology is that the average is an estimator and the expected value is what we want to estimate, and that is sometimes called an estimand. Now here for this whole logic, it doesn't matter whether x is continuous or discrete. All that matters is that there's a distinction between these two things. And of course, I get a sample with n observations and draws from that distribution. I calculate an average. I get another sample with some other n draws from that same distribution. And I will, of course, calculate another average. But these averages are actually not going to be too different from one another if n is reasonably big. And at the same time, what one can actually show is that when I get more and more draws, that difference becomes smaller and smaller. And in the limit, when I get infinitely many draws, my average is going to be very close actually to the expectation. So my estimator is going to be very close to my estimand. Next thing I want to recap is how we work with expectations. So suppose we have constants, little a, little b, and little c. Here, a, b, and c. And random variables x and y. Okay? Then what I can do is I can look at the expectation of a linear combination of the random variables x and y. So that linear combination is going to be little a plus little b times x plus little c times y. And what is the case now is, and that's a property of expectations, that this is going to be equal to a plus b times the expectation of x plus c times the expectation of y. Let's think of an example. So we have people, their little eyes, so I just indexes people. And they spend money on their apartment, apples and oranges. Okay, prices are fixed, so the rent is A, the price of an apple is B, the price of an orange is C. So total spending is a random variable because the consumption of apples and oranges varies across people, or at least this is how we now imagine it to be, because we can't really explain it. It's simply in our data. Okay. Now, its expectation is equal. So it's the expectation of total spending is equal to the rent plus the price of apples times the expected number of apples plus the price of oranges times the expected number of oranges. And of course, if I only have a sample, then I'm not going to observe these expected numbers of apples and oranges, but I can again estimate the expected number of apples and oranges by simply taking the average number of apples and the average number of oranges. What is happening here is that we use something that's called the linearity of expectations property. Conditional expectations. So far I had like random variables that were one-dimensional in the sense that, like we could think of x, y, and z as being sort of separate from one another. Now let's switch gears and think of data points as multi-dimensional objects that are still independent observations from one another. So I get a draw of a bunch of random variables for observation 1 and a draw from a bunch of random variables for observation 2 and so on and so forth. And they always come from the same distribution. Example. Your data contain a random sample of individuals, and I, again, indexes individuals, so runs from 1 to n. And for individual I, you observe gender. That's going to be xi. And that's going to be, for instance, coded as 0 for male and 1 for female. And income, yi. And income is going to be in euros. And these are draws from the so-called joint distribution of x and y. Okay, so for each individual I get a draw of x and a draw of y, and these draws are related to one another, so therefore the joint distribution. And once I have a joint distribution, it's meaningful to look at a conditional expectation. So for instance, the expected income for a given gender. And that's going to be denoted by the expectation of y. If the gender now is x is equal to 0, means male, so that would be the expectation of income given that somebody is male. And we can estimate this conditional expectation by simply taking the average income among males. Then there's something that is called the law of total expectation. And in this example, what that means is that the overall expected income is actually equal to the probability that someone is male times expected income conditional on male plus the probability that someone is female times the expected income conditional on female. So when you think about this, then this is a very intuitive property. Variance. So far we have looked at means, expectations, conditional means, conditional expectations, mean and expectation, that's the same thing. That's sometimes called the first moment of a distribution. A second moment is the variance. And the variance is a measure of dispersion. So how is it defined? It's defined as the variance of x is the expectation of the squared difference between that value of a random variable and its expectation in expectation. So I take the random variable, I take the mean out basically, then I square it, and then I take the expectation of that squared quantity. And I can estimate the variance by the sample analog of that quantity. So that means that I'm looking at this thing here, and here I have two expectations. Okay, sample analog typically means that I'm going to replace expectations by averages. So what does that mean here? I replace this expectation by the average, and I replace that expectation by the average. So what am I going to do? First step, I'm estimating the average of x. Let's denote this by x bar. I subtract the average from the observations. So I'm, sometimes one calls this demeaning, but I'm taking that average out, and I'm then squaring this quantity, and I take the average actually of the squared quantity. Okay, so the xi minus x bar is calculated here, and then I take the average. The standard deviation is very closely related, and it's simply the square root of the variance. So notice that, of course, I'm taking here the average of something that's squared, so that's always going to be positive. So I can definitely take the square root of that, and I've written it down here. The standard deviation of x is simply the square root of the variance of x. And there's also something that's called a conditional variance. The only thing that's really different is that one would do all that conditional on, say, a value of some other random variable. Next to the variance, there is something called the covariance. And again, when I have like two random variables, x and y, and they come from a joint distribution, and I have these draws that are always draws of x together with draws of y, then I can use this to measure the dependence between two random variables. So the dependence is going to be measured. One measure of that dependence is the covariance. The covariance between x and y is defined as, and there are various ways in which one can rewrite that, the expectation of x minus its mean times y minus its mean. Okay, so I'm demeaning x, I'm demeaning y, and then I multiply the two with one another, and then I take the expectation. And again, I can estimate this using the sample analog. So I take my observations of x, subtract the average of x. I take my observations of y, subtract the average of y, and then I always calculate the product of these two quantities, and then I take the average of all that across observations I. Related measure is the correlation. The correlation is defined as the covariance, and then we're going to just rescale that. So we're just going to divide by the standard deviation of x and the standard deviation of y. And the advantage of that is that we end up with a measure that lies between -1 and 1. So -1 is a perfect negative correlation. That means, you know, when x is high, then y is low, and vice versa. The correlation of 1 is a perfect positive correlation. So that means when x is high, then y is high, and vice versa. And a correlation of 0 means that there is actually no relationship between these two random variables, in the sense that knowing x will not help me to predict y. That is again related to statistical independence. So intuitively, if knowing the value of x does not help you to say something about the value of y, then both are said to be statistically independent of one another. More formally, the distribution of y does not vary when I have different values of x. So be a little bit careful here. It could be that, for instance, the mean of y does not depend on x, but the variance of y does depend on x. So in that case, we would be able to say something about the distribution of y when we know the value of x. So then, in that case, even though the mean of y does not depend on x, we would have that the two are not independent of one another. Back to the example where y are wages and x is gender. So again, 0 was male and 1 was female. So here, independence of x and y would imply that the expectation of the wage, conditional on x is equal to 1, is equal to the expectation of the wage, conditional on x is equal to 0. So that would then simply be the expectation of the wage. What this is mean independence. So here, in this example, I have the case that knowing x does not tell me anything about the mean of y. But then again, be careful. So it could be that there's mean independence, as we have it here in this example, but not full independence. So it could be still that the variance of y does depend on x. So the variance of wages would depend on gender. So it's simply important that one is always aware of this. And then finally, independence implies mean independence, a zero covariance and a zero correlation, but implies always means it's sort of a one-way street, right? So it's not necessarily going the other way around. Okay, so it could be that we have mean independence, but not full independence. It could be that we have zero covariance, but not independence. And it could be that we have zero correlation, but not independence. Now, to make it even more complex, these three things here, mean independence, zero covariance, and zero correlation, are at the same time actually very much related to one another. So for instance, if I have a zero correlation, then that is the same thing as having a zero covariance. Okay, so a zero covariance will imply a zero correlation, and a zero correlation will imply a zero covariance. Why is that? Because, the correlation is simply a rescaled version of the covariance. And also, mean independence is actually closely related to a zero correlation or a zero covariance. Now let's think of an example in which we have a zero correlation but not independence. So one example we had before was the one in which the variance actually does depend on x. Another example is this one here. So what do we see here? We see here draws of xi, and we see draws of yi, and they look like this. Okay, so how have I obtained these draws? I've simply taken a parabola. The low point was at x is equal to 5, and then I've just added some noise to it in the vertical dimension here. And if I simply generate data here, 1,000 observations, and calculate the correlation, then I end up with a number that is essentially 0. Okay, so it's a correlation of 0.0089, so that's really close to 0. Now, how can one see actually from these data points already that the correlation is going to be very small? So one sees basically that there are about as many observations here as we have here. Okay. So if one would fit a line through the data, basically predicting y using x, it would be a straight line. So the slope would be very close to 0, and a 0 slope in fact corresponds to a 0 correlation. And that has to do with the Ols formula that you might have seen before. So the Ols formula says, the slope coefficient is the empirical covariance between x and y divided by the empirical variance of x. And if the slope is very close to 0, then that must mean that the empirical covariance between x and y is close to 0. But if the empirical covariance between x and y is close to 0, then also the correlation is going to be close to 0. So it's not completely unexpected that I'm going to find a correlation that is close to 0 when I can imagine the slope to be very close to 0. Now, this all shows that there's a 0 correlation in my data here. But at the same time, and this is an example that is meant to illustrate this, independence does actually not hold. So we have a 0 correlation, but we do not have independence, right? Why is that the case? Because mean independence does not hold. So on average, I see that when I know that x is, say, 20, then on average, y is going to be something like 250, right? So I see that here, and when x is about 5, then on average, y is going to be 0. So mean independence does not hold. So I've written also here for different values of x, we actually do predict different values of y. So mean independence does not hold. And again, here I've written down that the expectation of y given x depends on x. Okay, and this can't be when x and y are independent. So again, this is an example where we don't have independence, but we have a 0 correlation. Now let's move to what is usually used in econometrics, and of course regressions are not only used in econometrics, but we use them a lot in economics and econometrics. There's one thing that is different than in other disciplines, and that's that very important distinction between causality and prediction or correlation, if you like. Let's quickly recap how one can think about regressions. So one can think about them as a convenient tool to estimate conditional expectations. Let there be observations x, y. So here I've written them as xi, yi for individuals I, again going from 1 to n. And they're all drawn from the same joint distribution, so joint for x and y. Okay. Let's specify a linear model, and linear here means linear in the parameters beta 0, beta 1, beta naught, and beta 1. Beta naught is sometimes called the intercept and or the constant term, and beta 1 is in this case here the slope coefficient. How do we call things? So yi is the so-called dependent variable or left-hand side variable, and xi is the independent variable or regressor. And here what we do is we actually regress y on x. That's important. We don't regress x on y, we regress y on x. Just keep that in mind. Here I've written that beta naught and beta 1 are the parameters that we want to estimate. These are unknown. And epsilon I is called the error term. Sometimes that's also called the disturbance. And epsilon I captures randomness across individuals that we can't quite understand, right? So there's something like a systematic part of the model, and that would be beta naught plus beta 1x. So that is sort of what is predictable in terms of what is happening to y, and epsilon I is something that is unpredictable. We carry out regressions by using the ordinary least squares estimator. So we have this regression model on the previous slide, and we have these two parameters that we wish to estimate. And one way to do that, and there are many other ways, but the most prominent and the easiest way to do that is to minimize the sum of squared deviations from the model prediction. Okay, so the model prediction is what I'm going to predict using x, and then I have my data, I have my yi, and I take the difference between my yi and my prediction, and that's going to be squared. Okay, and what is squared is also sometimes called the residual. Okay, so think of it as solving a minimization problem, even though we actually don't literally do that when we use that estimator. Let's pick some candidate parameter values, beta naught and beta 1 tilde. Okay, calculate predicted values for yi as beta naught tilde plus beta 1 tilde times xi, and do that for all I. Then calculate the deviation between the actual value of y and that predicted value. Square all these deviations and sum them over all i's. Okay, and then find, so that gives us a value of a criterion function, a goal function. Okay, and then what we do is we find the candidate parameter values that actually minimize that sum of squared deviations. So I said that we're not actually doing that in practice. The reason is that there's actually a closed form, right? So once I have my data, I can simply do this all in one go. So it's basically one line of code if you code this up in a computer program. All this gives us estimates. These estimates are going to be denoted by beta naught hat and beta 1 hat. And first of all, recall that before we have made this distinction between estimators and estimants. So these are going to be the estimators of our parameters of interest, and these parameters of interest are our estimants. Now, one can show that in a somewhat artificial standard situation, beta naught hat plus beta 1 hat times xi is what is called the best linear predictor of y, and it's best in the sense that it gives in expectation a correct prediction. So if one does this many times for many samples, then one gets on average a correct prediction, and it does minimize actually the variance of the prediction error. And again, the variance across samples. So when I'm saying here across samples, then it always means, I get a data set, I do my estimation exercise, I get estimators, I calculate the difference between my estimator and what I want to estimate, and that's hypothetical because I never know that in practice, but hypothetically or conceptually one can do that, and then I'm just looking at the variance of the prediction error. And that is actually related to something that's, so this set of slides here is called Econometrics for machine learning. So the mean squared error is a very important quantity in data science. Here we look at unbiased estimators. And in that case, the mean squared error is actually going to be one-to-one related to the variance of the prediction error. Now, now we enter core econometrics territory. So now let's first interpret the results of a regression as a prediction. Okay, so recall that yi is beta naught plus beta 1 xi plus epsilon. And we have these estimates, right? Beta naught is estimated by beta naught hat, and beta 1 hat estimates beta 1. What we can now do is we can think of beta naught hat plus beta 1 hat times xi as estimating the conditional expectation of y given that x is equal to xi. So what we do here is we predict the mean of y when x takes on a particular value, namely xi. And what's important is that we don't have to make any distributional assumptions for epsilon for this. And in particular, we do not have to assume that epsilon is independent of x, for instance. So exogeneity, and this comes on the next slide, actually does not have to be assumed. So we can just do that, right? We can just take data on y and x and estimate these two parameters, beta naught and beta 1, and then we can use it to do predictions, right? And the Ols estimator is meant to do exactly that, to give us the best possible prediction. Okay. So again, let's look at an example. So now let's take wages, yi, and education. Okay, education is now coded as, or xi is now education. And in particular, I'm going to say that xi is equal to 0 if people did not go to university, and is going to be equal to 1 if people did go to university. Then I can take wages. I can take a data set in which I have two variables, wages and education, coded like this. I can run a linear regression, so I can run Ols, and afterwards I can predict what wages will be for those. We can predict wages for those who did not go to university simply by using this formula. So I'm going to use beta naught plus beta 1 hat times 0. So it's going to be beta naught hat. And I can predict wages for those who went to university. So it's going to be beta naught hat plus beta 1 hat times 1. So it's beta naught hat plus beta 1 hat. So the difference in wages, in predicted wages, is estimated to be equal to beta 1 hat. Okay, so in the end of the day, what I'm doing here is I'm simply estimating two averages. I'm estimating average wages for people who didn't go to university, so that's going to be beta naught hat. I'm estimating average wages for people who did go to university, that's beta naught hat plus beta 1 hat. So, the difference between these two averages is actually beta 1 hat. Or put differently, instead of running Ols, I can simply calculate two averages, average wages among college graduates, average wages among those who didn't go to college. And I know immediately how I can translate these two averages into estimates of my parameter values, namely using these formulas. Okay, so the average that I'm estimating for the college non-graduates, I'm just going to call beta naught hat, and the difference between the two I'm going to call beta 1 hat. All right. Now comes a very important step conceptually. So it's about interpreting the results as causal effects. So again, consider the bivariate case in which this is my model. This is my regression specification that I'm using. And again, I have these beta naughts, hats, and beta 1 hat. And these are my estimates of beta naught and beta 1 respectively. Now, and this is something that you might have seen before. So when this is the model here, with an epsilon specified simply like that, okay, then it's always the case, again, without making any additional assumptions, that beta 1 hat will estimate beta 1 plus this term here, okay, plus the covariance between x and epsilon divided by the variance of x, okay. That is always true. So what that means is that when I go back to this slide here, that something is actually going on with respect to the relationship between, say, beta 1 and beta 1 hat. Okay. So here I said our estimate of beta naught is beta naught hat, and our estimate of beta 1 is beta 1 hat. That is still true. I haven't said what exactly the relationship between these two things is. Here I have now written down what exactly the relationship actually is. So when I get many observations, then my estimate beta 1 hat will actually be very close to this quantity here. So it's the true beta 1 plus this term here. Okay, so what I'm going to pick up as, intuitively speaking, as the difference in wages between college graduates and college non-graduates is going to be the sum of two things. One is beta 1, and the other one is this fraction here, the covariance between x and epsilon and the variance of x. What are these two things? Beta 1 is the true causal effect of receiving university education, and this thing here is related to what is sometimes called omitted variables bias. Okay, what that means is when I'm comparing wages between these two groups, those who went to university and those who didn't, then the difference between the two average wages is on the one hand the effect of college education on wages. So you learn stuff when you go to university, and that makes you more productive, and therefore you earn more. Plus this term here and this term here is related to something that is called selection into college education. So it means that those who actually go to college would on average earn more or less anyway, even if they would not go to university. So if the covariance between x and epsilon is positive, then it does mean that those who go to college would also have earned more had they not gone to college. So this is all conceptually not super straightforward, but at the same time it's really at the core of econometrics, and of course one spends usually a lot of time on understanding this better. Now, one step back. So I've said, this is my regression model. In any case, beta 1 hat is going to estimate this quantity here. So it's going to estimate the sum of two effects. And now comes the exogeneity assumption. So now assume in addition that epsilon is mean independent of x. Okay, so the expectation of epsilon does not depend on x and is equal to zero. And this is one way of formulating what is called the exogeneity assumption, and it's a very important assumption that is often made, and it does, for instance, hold when xi is randomly assigned. Okay, so for college education that is not realistic, but for other things it would be realistic. So think of clinical trials where some people receive a treatment and other people receive a placebo. So when x is randomly assigned, then what we will have is that the covariance between x and epsilon is equal to 0. And therefore, beta 1 hat will actually estimate beta 1, as this quantity here is going to be equal to 0. So back to the wage example. I've already talked about it. Without exogeneity, what we can do is we can estimate the difference in wages between those who went to college and those who didn't. With exogeneity, so if we could in principle randomly assign college education to individuals and thereby circumvent the selection problem or selection into college education, then we could actually estimate the effect of college education on wages. Why is that such a big deal in econometrics and economics? Well, it's a big deal because when we can estimate the effect of college education on wages, then we can think about the question whether we should encourage more people or other people to actually attend college, right? Otherwise, if we can't really estimate the effect of college education on wages, but simply compare average wages between those who went to college and those who didn't, then it's an apples to oranges comparison, in the sense that people who did go to college are actually not comparable to people who did not go to college. So we can never really know whether that difference in wages is reflecting an effect of college education on wages, or it's simply reflecting that these two groups of people are different from one another. So far, I've talked about the bivariate case in the sense that there was one y and one x. There's a straightforward extension, and that would be a multivariate regressions. So what one would then have is, again, one y, but one has multiple x's. Here I have capital K x's, and they're denoted by x sub 1i up to x sub ki. Otherwise, the model is the same, and one would also do things in a very similar way if one wanted to estimate these parameters. Again, one could minimize the sum of squared residuals. Yeah. So let's look at an example. that again, yi be income. Let's look at some examples of regressors or right-hand side variables. So age I is age in years. Female I is an indicator for female. And then there's a so-called interaction effect that would be the product of age I and female I. Okay. And you know, when we have all that, we can write down the model that looks like this. So yi is beta naught plus beta 1 times age I plus beta 2 times female I plus beta 3 times this interaction effect between age I and female I. So technically what you'll have in your data set is actually 1, 2, 3 variables. And depending on the implementation, sometimes a fourth one that would be simply 1 for all observations, and that is the regressor, you know, belonging to that intercept or constant term. Okay, so now let's look at males. For males, I can take this equation here and just substitute in that basically female I is going to be 0, so it's going to be 0 and it's going to be 0 here. So what I'm going to end up with is yi is beta naught plus beta 1 times age I plus epsilon I. Okay, so I'm getting my estimates after running OLS. So what that will mean is that beta naught hat is, just looking at this, the predicted income for males who are 0 years old. Okay, at birth. That's somehow, of course, a little bit hypothetical because nobody earns income, but you have to think about it in terms of, you know, this regression line and where this then hits the vertical axis. Beta 1 hat is how much predicted income changes for male individuals who are 1 year older. And we see this by simply looking at this equation here. So beta 1 is the coefficient on age for males. Okay. Now let's look at females. And that tells us something about beta 2 and beta 3. For females, I can write down this equation here. So I'm simply substituting in a 1 for females. So I'm getting beta naught plus beta 1 times age plus beta 2 plus beta 3 times age plus epsilon I. Okay, so what that means is, again, looking at my estimates, beta naught hat plus beta 2 hat is actually the predicted income for females who are of age 0. So just compare this to what we had for males. So for males it was beta naught hat. So that means that beta 2 hat is the difference in that predicted income in the intercept term between males and females. Maybe more interestingly, beta 1 hat was how much predicted income changes for male individuals when they get 1 year older, when they're 1 year older. Now, for females, just looking at this equation here, what we see is that, you know, beta 1 hat plus beta 3 hat is how much predicted income changes for female individuals who are 1 year older. So what that means is that beta 3 hat is the difference in that change in the conditional expectation when I increase age by 1 year between females and males. Okay, so for males, that conditional expectation increases or decreases by beta 1 hat, and for females, it changes by beta 1 hat plus beta 3 hat. So beta 3 hat is the estimated difference in the change. Now let's look at the interpretation for other dependent variables on this slide here. Again, consider a simple bivariate model. Yi is beta naught plus beta 1 xi plus epsilon I. So if yi is continuous, like the level of income, then the slope coefficients, or here slope coefficient beta 1 or beta 1 hat, then which will be the estimate of beta 1, is estimating the difference in conditional expectations of yi when xi changes by 1 unit. Okay, so in the income example, this was a difference in expected income. Okay, if yi is discrete, and in particular, if one codes it in a smart way, namely 1 for yes and 0 for no, then what the slope coefficient will estimate is actually the difference in the expected fraction of yes when xi increases by 1 unit. Okay, so let's think about this for a moment. If yi is actually something like yes, I went to college, then I code it as 0 and 1, and I just take the average, then I actually get the fraction of people who went to college. Okay, and if I regress, therefore, that 0, 1 thing on x, I get the change in that fraction of people who went to college, for instance, when x is something like, if I live in a city, or if my parents live in a city, or if my parents live somewhere in the countryside. And here, there's one thing that is also going on, which is that I said before that an average estimates an expectation. Actually, a fraction of observations is also an average. And the expectation that is actually being estimated, an expected fraction, let's say, that will be a probability. Okay, so a fraction does actually estimate a probability. So the probability is the estimand, and the estimator is the fraction here. And I can code yi as 0 and 1, and then what I'll get is actually estimates of coefficients on x, and as this is basically estimating how the probability that yi is equal to 1 changes when x changes. So it's quite useful, and this thing is called a linear probability model. Finally, a super useful specification in many contexts, and also one that works really well when one has data on something that is continuous and positive, strictly positive, so bigger than 0, is to not use the value of something on the left-hand side directly, but to use the natural logarithm of something on the left-hand side. So here I've written it down for the natural logarithm of income. Okay, when I put the natural logarithm of income on the left-hand side as my y, then what we're going to actually estimate is how that natural logarithm of income changes when I change x. Okay, and an important result here is that the changes in the natural logarithm are actually approximately equal to percentage changes or percentage differences. Okay, let's look at this in a little bit more detail. So let's say B is average income when x is equal to 1, xi is equal to 1, and A is average income when xi is equal to 0. Let's assume that the percentage difference when xi increases by 1 unit is a little g. Okay, so what that means is I'm saying that B divided by A is equal to 1 plus g, and g is something like a growth rate. Okay, so let's take this as the starting point. B divided by A, so B relative to A is 1 plus g. Okay, and g is that percentage difference. If I take the natural log of both sides of this equation, then I'm going to get the natural log of B divided by A. So that's going to be the log of B minus the log of A. And that's going to be equal to the natural log of 1 plus g. Okay, and you can try this out in a computer package, computer software, or yeah, in any way you like numerically. So close so when G is not too far away from 0, so when I'm looking at growth rates in the order of 2, 3, 4, 5%, so 3% would be 0.03, by the way, then we have that the log of 1 plus G is approximately equal to G. Okay, so that means that the log of B minus the log of A is going to be approximately equal to that percentage difference or growth rate in some other contexts. Consequently, when I regress the log of y on the level of x, then I'm going to estimate the effect of a change in xi by 1 unit on the log of yi, and that is going to be directly equal, approximately at least in the sense here, to little g. Okay, so when I'm finding a coefficient on xi, an estimate of a coefficient of 0.03, then that means that, and yi is the log of income, it means that income, not the log of income, income is 3% higher when x increases by 1 unit. And that is super useful because percentage differences or percentage changes are so-called unit free, so we don't need to understand whether something is a big or a small effect, right? So if I tell you that somebody earns 12% more than somebody else, then I understand that this is quite sizable. When I tell you somebody earns so and so many euros more than somebody else, then it always depends on the context whether this is a lot or not. So for instance, it depends on whether I'm looking at monthly income or yearly income. But of course, when I look at percentage changes, they will be the same for monthly income and yearly income, at least when I'm earning the same in each month. But absolute changes would be multiplied by 12. So I'm telling this here because it's a useful thing to use in practice. Oftentimes log specifications work really well, and oftentimes these linear probability models where yi is coded as 0, 1 also work quite well in practice. Finally, and that's also a super prominent and super important tool in the econometrics toolbox, that would be instrumental variables estimation. So consider again the simple bivariate model. Yi is beta naught plus beta 1 xi plus epsilon I, and let's just say xi is not exogenous. Okay, but I have access to an instrument that is exogenous. So that instrument would then be denoted by zi. And yi is that instrument affects yi only through xi, in the sense that that instrument zi is independent of epsilon I. Then what we can actually do is we can estimate the causal effect of xi on yi, not by regressing yi on xi, but by first using a linear regression with a constant term to predict xi using zi, and then to regress yi on that predicted value. And what I'm describing here is the so-called two-stage least squares estimator. This is how one can do that. There are other implementations of instrumental variables estimation. I don't want to go into details here. What I do want to stress is that this is a super useful tool in many contexts, also for data scientists. So this ends this presentation on econometrics for data scientists. I hope this was useful. With this, all the best.